Okay, tonight, last topic, which is WAN, wide area network, and the things we'll look at: WAN topology basics, access, connectivity basics, point-to-point protocol on WAN interfaces using local authentication. And there are a couple of labs doing these things. Uh, uh, Multi-link point-to-point protocol on a WAN. I always want to say multi-layer with that. And then point-to-point protocol over Ethernet, client-side interfaces, and kind of what we're talking about here at DSL connections. GRE tunnel connectivity, and then single home branch connectivity, single home, dual home, whatever. But WAN, obviously, as down here in the image, is going over long distances. And we use different layer 2 protocols here. That's what PPP, point-to-point protocol, is all about. The Cisco proprietary default, or the Cisco default, is a proprietary protocol, HDLC. One of my very first CCNAs years ago, uh, you're connected with a Cisco to a 3Com or whatever other router, and you get an up-down when you do a show IP interface brief. And the issue was that the Cisco router was configured with HDLC and the other end was PPP. So it was just a matter of going into that interface, the WAN interface, and changing the layer 2 protocol, encapsulation PPP. Simple command. You just have to know where these things go. And that's what this stuff is about. So WAN technologies that we use to make things better: VPN, frame relay. Again, I'm not going to talk about frame relay because, as I said earlier and in the course and earlier today, it's not there anymore. I have taken out all of the slides, and when I put the labs up, I may have already crossed them out. If not, I'll cross them out. I don't think there's any need to do it. It's a moderately complex configuration, unless you're just doing the client, in which the ISP tells you exactly what to do. But VPNs have reduced cost and probably improved security for people moving around, because what it gives the users the opportunity to do, employees the opportunity to do, is if they're traveling, to connect using a client back to the corporate headquarters via a VPN and have an encrypted session, so that it's not as insecure as others. What we're talking about here, security protocols implemented on both ends of an insecure network. We're sending an encrypted connection. We like to draw these nice, cool pipes, but they're really not. We'll draw them like a router here and a router here, and then we'll create this really cool tunnel. Well, there's a whole bunch of routers in here. There's more than one hop. We're probably not going to be connected directly. So what we do is have an IP address on the outside and then an encrypted packet on that. We have to have this IP address so that it can go through the routers. Once it gets to the other end, this stuff's all stripped off and it's decrypted in order to create that encrypted connection. Asynchronous transfer mode, cell switching, multiplexing technology provides data link layer 2 services with scalable bandwidth, usually over synchronous optical networking. I think when we're talking about those, we're really kind of talking about voice, high-speed voice in a lot of instances. And then frame relay, packet switch network, that we're not going to talk about. The WAN topologies again, and we'll look at each of these. Allows you to specify the peers on the network that are part of the WAN topologies, get access to policies to apply your WAN configuration methods based on the assigned IPsec technology. One of the things here, we talk about a hub and spoke, and let's draw a hub and spoke here, or try to. I went way off the page, didn't I? A hub and spoke here. This is the hub we have IP addresses here, and we do network protocols. Let's say we do EIGRP group 100, and then we advertise our networks. And here we do EIGRP 100, and we advertise our networks. And here we do EIGRP 100 and advertise our networks. And all of a sudden, these guys only have the directly connected and the networks that are on this router. Same here, because we have this thing called split horizon. And probably what we're doing, and I drew this poorly, should come to a point, is we have sub-interfaces here. So if we have a sub-interface, a .1, a .2, or whatever sub-interfaces, we send a routing update in. It goes in on the physical interface. It then can't go out on the physical interface. And that's where the no split horizon command comes in. That's kind of some of the things we're talking about when we talk about configuration methods. Based on the assigned IPsec technology that they talk about here. The IPsec technology for VPNs, I'm talking here about WAN topologies, the hub and spoke topology with this thing. We have point-to-point topology, pretty straightforward, usually serial link from one to the other, and then a full mesh topology. Full mesh is going to take an awful lot of connectivity if you have very many sites or very many IP addresses to go to. So slides on each of these things. The point-to-point, the simplest topologies, a customer will be able to connect two sites with an access link. Maybe we're going to use lease lines, maybe we're going to use the internet, maybe we're going to use a VPN, a number of different ways. If you use the internet, you really should use a VPN because it's a public networks out there, stuff just running around doing whatever. Allow two customers to send Ethernet frames to each other, and we can encrypt the Ethernet frames or encapsulate the Ethernet frames in other protocols. I'll get my tongue going here in a minute. For this topology, the router is to become neighbors and exchange routes. The routers must use physical Ethernet interfaces and be configured on the same IP subnet. Nothing magic about that. That's what we have been doing. The hub and spoke, we have a central device, and then they have leaf sites, or the spoke sites, remote or leaf sites or spoke sites, send Ethernet frames directly to each other. The remote leaf sites will be able to send the Ethernet frames only to the central site. We'll send them here, and then they have to send it out. And this is one that you may get into with split horizon. And that's just something, I'm not saying you will, but that's just something to be aware of if you start having issues with route tables not getting to the remote sites and they're not being able to share routes when you do those things. Central site serves as the root. With each remote site will be one of the leaves, and the topology is also referred to as a partial mesh, hub and spoke, point-to-point. All of these are point-to-point connections. Partial mesh, this one really, I guess you could call it a partial mesh. If I were going to call it a partial mesh, I would do a couple of other things here. Or one other thing. If I was going to do a partial mesh, we do this, because everybody connected to everybody else. If we go something like this, I think we'll probably have pretty close to a full mesh here, don't we? Connected, 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 connected. Lots of bandwidth. If you're going to do a full mesh, the thing that we're not going to talk about, frame relay, is a protocol that actually will allow you to do that. But partial or full mesh is going to be relatively expensive regardless of what we use, and lots of bandwidth that goes in here. And this is the full mesh, and down here I've added this formula of how many do we need. So n nodes, point-to-point connections, n times n minus 1 over 2. So we have the 4 times 3 over 2 is going to be 6. 12 over 2 is 6. So do we have that 1, 2, 3. This one's not a full mesh, is it? We'd have to do this to make it a full mesh. 1, 2, 3, 4, 5, 6. Okay, not so bad. But let's say that we have, oh, I don't know, 10 sites. So we have 10 times 9, n times n minus 1 over 2, 90, which is going to give us 45 different connections. Now we're starting to talk about some serious configuration when we do those. So a WAN, full mesh WAN topology, creates a direct communication path for a set of devices. Useful if the enterprise needs to connect several sites to the WAN with the goal of allowing every site to send a frame directly to every other site. And they did this, and they really didn't create a full mesh here, because A and C are not directly connected and B and D are not directly connected. When we connect them, then we have an entire, this would actually be a partial mesh, a full mesh topology when we connect those together. Each device sends directly to every other device as if the WAN service were one big Ethernet switch. So lots of reliability there, but lots of, I think, complications if you have a whole bunch of sites in your system. Single homed, and this is with single homed and dual homed. And one of the things I read said, know the difference between single homed and single homed and dual homed. So single homed, single link to the ISP, to the enterprise network. Only one ISP, must be only one ISP, and that kind of makes sense. If we only have one link, we're going to have one ISP. Must be only one ISP, and this link must be the only connectivity to the ISP. To connect an enterprise branch to the internet, allow various kind of WAN links, DSL, cable, fiber, Ethernet, or wireless LTE connection. So lots of different, and they are really kind of crazy about DSL. You may get some other, and I think that probably you guys have experienced other types of connectivity. I guess fiber being the thing that we would prefer now. If the link fails at either end, the internet's not going to be accessible. No big surprise there, just looking at the diagram. So we have that, and then we have the dual home. This one is kind of, and we'll talk about a different dual home in a little bit, but dual home, 2 links between the ISP and the enterprise. So we have 2 links. If the ISP has a problem, and they have had issues before, if the ISP goes down, we're still out of luck. 2 links provides an alternate path for reaching the ISP, and if you go back to HSRP, we could do that if we configured, and we looked at HSRP at our end. If we had a failover protocol going to the ISP, we get a similar circumstance with failover. But if the ISP fails, we're still out of luck. Later on in this presentation, we talk about doing it ISP1 and ISP2, so that if one of them fails, primary, maybe your fiber network over here, and up here maybe you got cable modem as a backup to give you some connectivity should your main ISP have an issue and go down. So different things to consider in the dual home, but the difference between single homed and dual home, basically one connection or 2 connections with that. ATM, asynchronous transfer mode. First time a lot of people see this. No, it's not a place where you get money, but we have class of service, and what this is showing up here is we can divide things out. So up here in the red is real-time voice, and then we have best effort, bulk, business critical, and video. So we split out the link into different classes of service and the priority queues on these things, and goes back to some of the prioritization that we talked about. Uses one virtual circuit to carry traffic to the next hop address. Even in the case of multiplexing, a single virtual circuit is going to be used. multiple methods, weighted, random, early discard, weighted, fair queuing can be used to classify and prioritize the packets. Go back and look at the prioritization that we talked about. To share, we'll share one quality of service virtual circuit, this thing here. When you require permanent virtual circuits, configure the PVC in both the router and the ATM switch. And PVC and SVC, switch virtual circuit, permanent virtual circuit, and switch virtual circuit. Permanent stays on all the time. These come on an on-demand basis. A number of different images here about how we might hook this thing together, or how it might be hooked together. PVC, those are terms that you're going to see in ATM, and I'll go back to the one again we're not going to talk about, frame relay. Frame relay kind of uses ATM underneath. MPLS, multi-protocol label system. This is an attempt to make data switching, data forwarding, data switching basically faster. Here is a type of a data carrying technique for high performance telecommunications. Directs the data from one network node to the next based on short path labels. What we're doing here in the header is putting a shim in. I got an image here in a minute. Putting a shim in so that the devices don't have to look deep into the packet to find out where to which interface to switch that packet to, or that frame to, that we go through this thing. Allows you to combine the performance and capabilities of a layer 2 data link switch over this with the scalability of a layer 3. So we're going to read this label very early in the process. And you remember when we talked about switches, some of them we waited, some of them we started sending it as soon as things happen. And this is going to look in, and this shim gets put in before the layer 2 address to send it to the correct location. Flexible, can employ with many combination layer 2 technologies, layer LAN switching and WAN circuits. Support exists for layer 3 protocols beyond those typically used today. So what we're saying is we've got this thing, and it does provide information for these things. Protocol for speeding up and shaping network flows, allows most packets to be forwarded at layer 2, the switching level, rather than being passed to the layer 3 routing layer. Each packet gets labeled on the entry, and then we have the different equipments, and this goes back to all those other things that we have. Oh yeah, this sounds really cool. Well, you got to have the resources that actually support this thing in the configuration. So we have a CE here is a customer edge router, and a PE is a provider edge router, and then we have LSR label switch routers that it goes through, and when it comes out it gets all the labels stripped off at the provider edge router, and then gets sent to the customer. So all of the labeling is in the ISP cloud. The egress router removes the label and forwards the original packet to its destination. So we're going to label these things, and in order to speed it up, this is where we go, what we do with this thing. And I said it before the now this one is actually after, obviously. The link layer header, this would be the MAC address or the Ethernet layer header, and then the MPLS shim before the network layer. It's going to be 32 bits, label number that goes in it, and it has a time to live in here also. I don't remember what all the abbreviations are, but what these things are, we go in, and this is what one of the forwarding tables might look like. Label 102, pop label or tunnel ID 6.6.6.6, 32-bit Ethernet. The next hop 200.13.0.6, and then 103. Outgoing label is 603. It gives a prefix. These things get relabeled. To get an ingress label, get you there, and then you change the label before it actually leaves the device in order to go from location to location. This one, the ingress router, outgoing label is added to it, sent to the link label switching router here. Incoming label is replaced with the outgoing label, and it gets sent to the next one. And then we go to the edge router where it's stripped off and sent to the customer network. So a way to try to make things faster in the network. Metro Ethernet, when we talked about networks early on, we talked about LAN, WANs, and MANs, a metropolitan area network, and that's what this is. It's metropolitan. It is a metropolitan area. It is usually going to be a ring, but we have a cloud in here. The service provider, in the image, hopefully makes a little sense here. Access, aggregation, and core. What we're talking about here, we have the core of the network, aggregation around these, and then we have access to where we have the customer here, and then the provider, and then the provider ring here that communicates among these things. And this is just things like we may have the public cloud, that we're going to go to the public cloud, to the internet here. A branch office here, a private cloud. We talk about private clouds and public clouds when we do these things. Radio access network, a metro, and some cities have tried to put in free wireless throughout the entire metropolitan area, so they would connect to it. We have some residential subscribers may be there. A data center here, a corporate office, maybe government offices are going to go in here, but the service provider for the Metro Ethernet network, it's nothing really different than most other providers that we have discussed, talked about, have a little bit of perception of. It's just that he uses a different layer 2 protocol. MAN uses a different layer 2 protocol than does a WAN, and then does an Ethernet. So here's another image that has a whole bunch of stuff in it, just to show what it might be. It won't necessarily be that, but a lot of different things can be connected to a Metro Ethernet. Broadband point-to-point protocol over Ethernet. What we're talking about here basically is DSL. And here, specification helps you define how a host PC will interact with a common broadband medium, such as a DSL, digital subscriber link, a DSL modem. Implementation requires two standards, Ethernet and point-to-point protocol. We use both of them. The point-to-point protocol profiles continue the configuration information for a group of sessions. One of the reasons that we need the point-to-point protocol is for the security, so that we can have the username and password login or whatever we're going to use to authenticate the users that are going to be using this network. Contain configuration information. The profiles can define multiple PPOE profiles for a device to allow different virtual templates assigned to these things, and can be separated by configuration of PPOE from configuration of virtual private dial-up networks. So this is a frame format which kind of maybe makes some sense, but we have the PPOE frame, we have the ether type here, the checksum, source address, destination address. So we have the Ethernet frame here, and then we have the PPOE packet, which is going to have its information, or the point-to-point, the PPP packet, which we'll talk about a little bit later in this session. So we have here again the frame with the destination address, source address, type, and then the PPOE, we have encapsulation. This one maybe a little bit different. We have the point-to-point protocol tunnel here basically, and then we're using Ethernet over it, and it goes to the DSLAM. DSLAM, the letters digital subscriber link access multiplexer, so it's going to multiplex the connections of a lot of users, maybe home users. DSL modem goes to the DSLAM and then to the access server, the concentrator. Up here, different things that may be. We have a corporate, maybe a yeah, I don't know. It was a corporate. It looks like we have two corporates. Maybe a small business and then a home customers all going to the DSLAM. Then they go into the ATM cloud to an aggregator, an ISP, POP, a point of presence here, which then goes into the cloud. May go across different places, but different ways to look at that. GNS3, and we have over here the configurations. We have the customer and we have the ISP. If we go to this thing, and I keep doing these wrong. Console here. Bring the console back over here. We had a lot of up downs and so on, and I think what they said to do was to do a debug path. Debug. Because what we have to do is sign into this thing when it starts up. Maybe PPEOE. Oh, well. Anyhow, I guess that what I could do is show you the configurations, and you may have done these before. We do a show run. I have them here. I have gotten these things in so many different places. But what we hopefully have done here is configured a dialer on this thing. I had this going really good here today, and now I don't know what I did with all of my documents. But if we keep going, we have multi-link, bundle name authenticated. We have these things. So I'm trying to find out where I did anything. Maybe I didn't. Maybe I have a PPOE. I don't. Anyhow, what we have to do is configure dialers on these things. Let's see if I have the. That would be a quick way to show IP interface on it. Anyhow, I will figure out what I wanted to do with that on the break and show it to you. But what we're doing is configuring a dialer, authorizing, and then we're using a PPP as well as Ethernet. Maybe my VPN will start like it's supposed to. But an internet VPN, what we're doing here is sending an encrypted connection used for the enterprise to connect the businesses on the internet using a WAN service. We're sending across the public network and encrypting it. And this one kind of worked and kind of didn't work, because I got my access lists all messed up. You have to have access lists on these things to tell it what gets put into the tunnel. So if I go in here to the console and wait for it to start, this again, GNS3, what actually does uses the Cisco iOS's. So we're going to show crypto, I think. Now, see, I can't remember all of my commands. This is where the show crypto. I guess I didn't get enough of the show crypto. Right, so I show crypto IPsec. No security. So this one is not. I don't have any security associations. They usually come up the first time you do something. Maybe these things didn't keep my configurations. So we won't use that one either, but anyhow, what we're doing is sending an encrypted, unless I have a VPN done, but I don't. An encrypted connection across the internet. What this was supposed to do was to bring up an encryption here, and this is the issue that I have with GNS3. It says it saves things, and then you go back to use it and it didn't save things. So what we're going to do with these things, prevent man-in-the-middle attacks, and the best way really to prevent a man-in-the-middle attack, if you've ever tried using Knable, is to do encryption. It'll try to give you a key. And if you take it, then it can decrypt everything. But man-in-the-middle attacks get prevented, verified. The packet originated from a legitimate device, that we don't have somebody spoofing information for us. And then we're going to verify that the packet's intact and not changed, that what we sent was what got us there. Internet VPN faster and cheaper compared to private WAN solutions. We don't have to have dedicated lines for these things. VPN, an image here, point-to-point serial lease lines are being replaced by the VPN to go across the internet with an encrypted connection. The dynamic VPN is one, and hang on, let me stop. Okay, so I didn't start the recording. What we're talking about is site-to-site VPN. We talked about next hop resolution protocol, which is basically we register our IP address in the dynamic VPN, and when we do that, we can create connections from spoke to spoke in these things. And the next one was the site-to-site VPN. What all of those lines were before up there is that if we create these things back here are plain text or clear text. The encryption takes place as we go into the tunnel, and we have an access control list that tells the system which traffic to put into the tunnel and which traffic not to put in the tunnel. So maybe this is 192.168.1.0 network, 192.168.2 network. What the access control list would do would tell the system to put 192.168.1 to allow traffic from both of these, from 1.0 to 2.0, and then the other end allows it back. All the other traffic would just go out on the onto the internet. If you're using from the client, and we'll talk about this in a little bit, a client one, not everything needs to go through the tunnel, and so we have this thing called a split tunnel, which only the specific traffic goes through the tunnel. And that's where the access control list, access lists, again, allow us to do that. The configuration for a VPN looks something like this, and this would be the configs for the one that didn't work for me, and this was created by a device. And the access list 100, we have a remark link to router 1, we have an access list 100 permit, and this should be 192. That was one of my issues, my typos. 192.168.2 00255 192.168 1.0 0.0.0.255. And then we have a crypto policy. We have an MD5 hash. The authentication was going to be a pre-shared key, encryption 3-DES, triple DES, group 2, and then the lifetime of the of this key here. And then we have crypto, the crypto statement, ISACAMP key, Cisco 123, address 10.0.0.1, which is the public address of that particular router. And then we have a transform set, and then we go into mode tunnel, and tunnel is the one that goes from location to location. Two different types of communications here. One is tunnel mode, and the other is transport mode. Transport mode goes direct, encrypts the entire conversation. It goes from the client to the server, so that it's encrypted through the entire process. I'll try to get that one in when we do the break here in a few minutes. So the site-to-site VPN, IPsec defines a set of rules for creating a site-to-site VPN. It's an architecture, it's a framework, and in the framework we put in like the security algorithm, the triple DES. We could have used any others that were available there. Which hashing algorithm are we going to use? And that's why they call it a framework, because it doesn't specify the hash. It doesn't specify the encryption. We do that within that framework. It defines how the devices at both ends connect to the internet to achieve the goals of the VPN. The 4 steps. The sending VPN provides the original packet, the session key for encryption. Sending device encapsulates the encrypted data, and the sending device sends the new packet to the destination VPN device. The receiving VPN device uses the encrypted data, and the session key to run the decryption formula. And then we have our encrypted or decrypted information at the other end. So here again, site-to-site VPN tunnel, we draw these nice pipes, but what we're actually doing here is sending an encrypted packet across the internet, which means that it's got to have an unencrypted IP address so that it can go from router to router to get from location to location. Because it goes to the internet cloud, you know that's not going to be a direct shot. So we encrypt it, and then we add the header information, the IP address. And one of those things was, where are we going to send this information to? We're going to send it to 10.1. This one 10.0.0.1. The client VPN, called transport mode. In this case, we're using SSL port 443. The reason that port 443 is used for these things typically is because it's usually going to be open on the firewall. So the SSL protocol provides the alternative VPN technology to IPsec. Web browsers provide secure information. Do you ever wonder what makes SSL secure? If you didn't, let's pretend you did. Let's say that we have a client here, me, and a server here that may be, let's say, a bank. Your bank, my bank, anybody's bank. So we create an HTTPS request, https://www.mybank.com. When it gets the HTTPS request, this thing has two keys. It's an asymmetric key. It has a public key and a private key. Public key is just that public. Anybody can have it. And when we encrypt something with the public key, it can only be decrypted with the private key. So it sends us its public key. We then, our computer, our device, our workstation, client, creates a key here that we're going to use. It's going to become a symmetric key, because asymmetric encryption and decryption, symmetric encryption and decryption can be like 1,000 times quicker, literally 1,000 times quicker than public-private. So we got the public key. We create a session key here. We encrypt the session key with the public key, public with the session in it, and send it back to the bank's web server. It then decrypts the encrypted packet with its private key, because anything encrypted with the public key can only be decrypted with the private key. So now we have a session key. And we have both of us have the same key, pre-shared key, essentially. Symmetric key makes the connection faster. So how does it get to be that way? That's why at the end of these sessions with banks and other secure places, I'll say, to be safe, close your browser, because this session key gets killed at the end of the session. So if somebody is able to get it, they only can get the data from that particular session. So we're going to use SSL to encrypt these data. The Cisco AnyConnect is client software. There are a number of those. Microsoft uses SSL VPN client, SSL VPN connection also. The next one is a client VPN, IPsec client VPN, where we actually use an IPsec client on the device itself. Cisco has those too. We use those quite a bit so that we could work from home. And one of those things that if it's, you know, a Saturday morning or a Saturday afternoon and somebody forgot their password, you don't have to drive 20 miles in order to reset a password. You want to be able to do it securely, and that's where the VPN comes in. The ISAKMP, also called the IKE, is the negotiation protocol, allows the client on a remote PC and the adaptive security clients, the ASA firewall, to agree on how to build the security association. Once that happens, we have two phases, phase one and phase two. Phase one creates the first tunnel to protect the negotiation. So we build a tunnel to encrypt the negotiation to build a second tunnel, which is going to be the encrypted tunnel that we use, and they're called phase one and phase two of these things. Client to site VPN, nothing magic there. Unsecured traffic, secured traffic. If we go from the client to the VPN gateway, firewall, router, whatever we're using, everything on the back side is not going to be encrypted. If we use the tunnel mode, where we go from device to device, and firewall to firewall, router to router, then everything on our private network is going to be insecure. That brings us up to PPP. I think let's take a break right now. Let's continue with this point-to-point protocol, standard protocol. It is the one that needs to be used if you have Cisco with something else. If you have Cisco and Cisco, you can use the default layer 2 WAN protocol, HDLC. Otherwise, you need to do PPP. Told you, and I did have that experience on a CCNA, and this was a very early on CCNA test where I had two routers, a Cisco and a 3Com with somebody else, and when you do a show IP interface brief, you got an up down. The first up is the physical connectivity. The second one is the layer 2 connectivity. which meant that the two protocols, the layer 2 protocols, were different. Cisco was configured with HDLC, and the other guy was configured with PPP. So you just had to go into the interface and give the encapsulation PPP command. One of the reasons we want to use PPP, and the reason that we use it in the dialers there, was it contains the built-in authentication protocols PAP and CHAP. PAP, not so very good. PAP is plain text, unencrypted everything. CHAP got a little bit later on. I have a process, challenge handshake authentication protocol. You send your request, they send you a challenge message. You encrypt the challenge message with your password, random character string typically, and then you either get a yay or a nay. PAP, unencrypted username and password with them. But PPP, point-to-point protocol, is what we're going to look at here quickly, and how it works. Controls the process for each higher layer protocol that's placed above PPP, and provides easy integration and support for such protocols. So, password authentication protocol, don't use CHAP, the one that we want to use, that are supported here. The PPP process, we have link dead, link establishment. If the link establishment success, then we go through the authentication process. If it configured, it doesn't have to be configured. If it's configured, and then we get the success network layer protocol, we'll get failure, link termination, goes around and around. So the process of what goes on in the point-to-point protocol link establishment. Encapsulation of this thing, multiplex different network layers simultaneously, different network layer protocols simultaneously over a single link. Again, one of those things that's really cool sounding, and it is, but right now the only thing that we typically use is IP. You might run into IPX, but even NetWare in the later version used IP and not IPX. So do we need the different network layer protocols? Probably not. Is it there? Yep. Uses LCP, the link control protocol, to negotiate the link's properties, monitors the continuing availability of the link using echo requests and responses. So link control protocol is the one that negotiates the properties and monitors whether it's going to stay up. PPP provides network control, NCP network control, IP control, multi-protocol label switching, the one that we talked about a little bit earlier, Cisco Discovery Protocol processor. This is not the CDP that we're talking that we have talked about. This is a different variant. IPv6 control processor, open systems interconnection processor, and all this big list here, which it shows that it does have lots of functionality. It's a protocol that's been around for a long time. If you ever use dial-up, dial-up used PPP as its protocol. Put in your username and password, and then they got you into the, after all of the negotiation with the screeching, would get in, but it used the PPP protocol. To negotiate the properties of the related protocols, they're used to negotiate the properties that run on the system. The PPP format, flag, address, control information with protocol here, LCP, NCP, and this is a little bit different, kind of the same process that we saw before, but here we have establishing, link is up, establishing. LCP, link control protocol, state is open. LCP open, no authentication. It's going to go around and the link's going to be up. PPP needs to be brought down. Authentication failure, terminating. We have link up, renegotiate the LCP. The link is up, goes around. If the link control protocol fails, then it brings the link back down. So we have a number of different capabilities in it PPP. PAP, PPP PAP, Password Authentication Protocol, to inform the central site and remote devices that are connected to the site. Central site about the remote devices. PAP's enabled. Attempting to connect to the local device will be required to send an authentication request uses clear text for authentication. We'll send the authentication acknowledgement if the username and password are accepted, and exchanges 2 packets to complete the authentication. Down here, the client identifies themselves, the server does the verification. This is not a message, and then the client provides a password, and then we get authenticated if it's correct. So PAP, clear text, not a very good. It's one of the original authentication protocols that been around, and if you do a Wireshark and you see it PAP, it's going to show up easily, readily readable in the Wireshark. CHAP, challenge handshake, used to inform the site about the remote devices that are connected. We'll send a CHAP packet to the remote device when we want to do that. CHAP will request a challenge. All this has got words. The first part of the encrypted version, I've got a picture here in a minute that hopefully makes this clear. The first part contains the encrypted version of the ID, secret password, and a random number. The second part contains either a host name and a remote device or the name of the user on the remote device, and CHAP will exchange 3 packets to complete its authentication. So what happens in CHAP is step 1, we request a connection to the remote access server. The remote server sends a challenge, which is a string, usually a random string, usually a random value, sends it back to us. The remote user uses the password, so then we send a hash. It says encrypt, and I think it's actually a hash. We encrypt, well, I won't say encrypt. We encrypt the hash with our password to encrypt the challenge sequence, send the results to the server. It then uses the password that we have on file here to decrypt the challenge to see if it's the same. If the response is the same, then we get on. So this one encrypted, a little bit better ability to protect the usernames and passwords with it. Let's see, we got 15, 25, 30. Multi-link point-to-point protocol is a way to bind, and this shows two devices here, and this is another one of those labs that I'll try to get running because all my configurations went away. I have them, but they went away from the demos that I have. We bind these 2 devices together here, combine interfaces that are related to the entire T1 or E1 multi-link bundle. So if we have 2 T1s here, we would go from 1.544 to 3,000, whatever bandwidth. We bundle it together much like we did with Ether channel, except we're doing it at layer 3 here instead of layer 2. We can have minimum number of interfaces in the bundle required, all the same sorts of things that we did earlier. This gives us some redundancy. If one of these goes down, the entire bundle, the entire link doesn't go down. It will be reduced in speed, obviously. Single virtual interface that allows you to connect to the peer system, provides a single point for applying hierarchical queuing, shaping, policing, all of the things that we did earlier. Combination with the E1 or T1, choose the required number of bundles in this thing. Load balancing, it provides load balancing functionality over the multiple LAN links, so it's going to load balance itself. Hierarchical queuing is not performed on the individual links, but on the bundle itself. And then the bundle is the one that's going to do the load sharing among the individual interfaces on it. Another image here. The reason there's so many slides, I got a lot of pictures in here, but in this one, the multi-link allows you to bond two links to appear as a single physical link, again like we did with Ether channel. Reduces the complexity by making two or more serial connections appear as a single serial connector. The multi-link interface fragments packets across both links. What that does the load balancing across the links. T1E1 traffic the transmitter received over the link here. The multi-link point-to-point protocol emulator or router. Same thing here. The configuration for that, if I can find it, if you want to kind of look at it. This would be R1s. We do config T. We create an interface, multi-link 1, give it an IP address, point-to-point protocol multi-link, assign it to a group, and then on the interface, this creates the link, and on the interface is that we're going to use this on encapsulation, PPP, PPP multi-link, group 1, no shut, same thing on both of them. Create the down here, we're going to create it again. This is 13, 14. That won't work there, so that's going to be a 252. Then told you I make a lot of typos. So kind of a different, not all that complex once we create the interface. Here we tell it that it's going to be a multi-link, and then we assign it a group number to associate those interfaces with. That's what the configuration of this thing would look like. The guidelines supports T1 only, T1 and E1, which it says that we're going to be using this thing on serial interfaces. Enable PPP encapsulation before configuring the multi-link commands. Only the interfaces that belong to the same interface module, serial 01, serial 1, we had serial 01 and 11, didn't we? The same modules are going to be allowed to combine on these things. Same interface module can be grouped in the bundle. Maximum of 16 interfaces in a group. Maximum MTU 9216, which is going to give us a pretty fast serial link if we use that thing. And the maximums here, MTU will vary for OC3, the optical carrier. T1 and E1 interfaces are not part of the MF and T1, and the T1 interfaces are not part of them. The speeds are listed in that table down there, the different speeds we're going to get on these things. But if we had T3, 16 T3s, we're going to be going at a pretty good speed there. Minimum links mandatory. This is another one, just like in Ether channel, allows you to configure the minimum number of links needed to keep the bundle up. And again, yeah, you can do this and the bundle will go down, but why not keep it up and fix the link would kind of be my question about that. When PPP, which mostly used to increase the bandwidth between points, allows you to establish multiple links to the same destination in parallel, what we've said before, disables the network control protocols for the bundle until the required minimum links are available for the multi-link. This is if we are below the multi-link, and remember the NCP is the thing that kept the link up. So if we go below the minimum, it disables the NCP. When we go back to the network control protocol, when we get back to the sufficient number, it will re-enable it. Be activated when you add the new link. Disabled bundle when you remove the link from the bundle, and makes the number of links less. And that's what the minimum links is. If we go below that, then whatever protocols that we have configured are not going to be configured anymore. The individual links will still be there. This one kind of got thrown in. We'll do the slide, but I have looked on it and looked in the objectives, and I don't see the Microsoft point-to-point compression protocol as part of it. But Microsoft and Cisco actually do a lot of work together. Technique used to compress the packets, and I guess that's why we're talking it here, between Cisco and Microsoft client devices. Is used to optimize the bandwidth to support multiple simultaneous connections using the Lempel Zib based compression algorithm. 12-bit coherency count, and down here following when the decompressor detects a count to be out of sequence, the following error process sends a reset request. Compressor then flushes the history, and then it recompresses everything. The rest acknowledge packets used for synchronization without CCP, but consumes additional time with these things. IP address pooling uses a pool of IP addresses that allows the incoming interfaces to provide IP addresses through the IP control protocol. We kind of talked about that when we were talking about hot standby routing protocols, that if the interfaces had the ability to kind of like go find their own, but over here the flow, PPP link establishment, LCP authentication here, and then IPCP, where we're going to get the IPCP address negotiations used on point-to-point interface to provide the IP address to a remote node. So it's going to send it, and this is one of those that, yeah, if we lost a connection, we could change the IP addresses instead of having the HSRP and VRRP in those. Variety of sources, IP address are command line, exec level command, TACACS, DHCP, locally administered address pools. All of those can be used with this, but address pooling, IP control protocol, provide an IP address to a remote node going through this process. Authentication, this is the link establishment. We're going through the process here. LCP, authentication. IPCP provides the link back to the remote node. Multi-layer, multi-link point-to-point protocol. This is an image that's trying to show what it does. Interleaving feature allows multi-link encapsulation and fragmentation of large packets to smaller sizes, and that's going to hopefully overcome some of the delay that happens in the packets. Real-time packets are already small in size. We saw that with voice. I think was 20. It was like 20 megabits instead of the 1500. 20 bytes instead of the 1500 bytes. Will not be multi-link encapsulated. Will be sent between the fragments of the large packets. Interleaving, and interleaving is when we kind of weave the things together. CRT TVs used to be interleaved. Monitors used to be interleaved. And what it would do is paint half of the image and then come back and paint the other half of the image with these things. So we have topic one here, and then on down here we have topic one again, and then topic one. So it interleaves the frames, breaks them up, allows for the efficiencies that it needs. Provides special transmit queue for smaller packets that are delay sensitive back to the quality of service that we talked about. Weighted fair queuing. The weighted fair queuing on a multi-link works at the packet level and not the level of the fragments. So queuing, we've talked about that a little bit, and multi-link, or actually weighted fair queuing, keeps coming back and back and back. All interfaces that support it, such as the virtual interfaces, support weighted fair queuing, which is enabled by default on it. Point-to-point over Ethernet, another one of the ones that my friend at GNS3 decided to destroy for me. is an application commonly used for the deployment of DSLs. Let's see if I can find, probably not, to show you what the configuration looks like for it. And I'll look again in a second. PP point-to-point protocol over Ethernet provides the client-side support. We looked at that a little bit, and it's kind of like this one is sort of out of sequence, but it's not because there are multiple slides here. Establish the PP connections between two endpoints over a serial link. DSL connect from the house to the DSLAM to get access to the internet. Over ATM must be one permanent virtual circuit that will support the clients in this thing, will allow multiple sessions to run concurrently over the same PVC, and an ATM PVC can be a member of several dialer pools, and dialer pools are one of the things that have to be configured in PPPoE. Dialer pools go back to when we actually did use dial-up in order to do that, and then we have access control lists in order to determine which one of those would work or wouldn't work, and people would kind of do some odd things with it. I've got a lab here. It's I think the lab that I did have configured that I don't have configured anymore, where we have the customer here, the ISP, to give you an idea of what has to be configured. The ISP here, we've got the username, goes into the database, who we're going to let get onto the network, and then the IP pool, point-to-point over Ethernet pool, and then the IP addresses that are going to be given out. The virtual template 1 IP address goes to it. Maximum transmission unit here 1492 instead of 1500 because the PPEoE is going to take some space in the header, so you want to reduce the MTU a little bit. Peer default IP address, pool PPPoE, so that was the pool that we configured up here for IP addresses. And then authentication, CHAP, call in, get through with that. BBA group, PPEoE, virtual template 1, which we used before exit. And then interface, the gig, associate the group with the physical interface, no shutdown. The customer configuration, the interface, enable point-to-point over Ethernet, dialer pool number 1, and then the interface, the maximum MTU, encapsulation, dialer pool 1, authentication, PPP, CHAP, hostname, customer 1, and then the password that we have. IP route for dialer 1, the default route is going to go to dialer 1, and then on this one debug PPP authentication so that you can see what happens on that. I'll look for that one again while you're doing labs and see if it shows up on any of mine. So for PPE, the maximum payload support, you need to ensure that the physical interface supports an MTU of 1500. Probably want to reduce the MTU to be sure that it's going to work, and we have to have the dialers, and dialers again go back to when we actually did dial over physical analog lines. The client technology, topology, in these things, the authentication's 2 phases. The discovery phase, the client locates the server called an access concentrator over here. The session ID is assigned to the PPOE layer, and then the session phase, the point-to-point protocol options are negotiated, authentication is performed, link setups completed will function as a layer 2 encapsulation method, and then we have connectivity to get to we have connectivity to the ISP and to use our internet connection. ATM permanent virtual circuits is provided on these things. The virtual access is cloned using the dialer interface, and then the client allows one ATM PVC to support multiple PPoE clients. And that's we keep coming up, I think, saying basically the same thing over and over again. When we have multiple clients run concurrently on different PVCs and need to ensure that each client uses a separate dialer interface, while multiple clients can be configured on an Ethernet interface, need to ensure that each session uses a separate dialer interface and a separate dialer pool. It kind of makes sense that separate dialers we're going to have for each of our users, that each is going to log in using their own username and password, their own dialer for these things. The session initiation, client broadcasts the Active Discovery, PPoE Active Discovery PAD-I packet. Concentrator serves as the PAD-I packet, receives the PAD-I packet. It will send the PAD-O packet, and if you look at this thing, it's an awful lot like DHCP, and that's what we're doing, the session initiation. We initiated on this virtual interface. We're trying to get started. We're trying to get the IP address that it told us that to get from it. So we send a PAD-I initiation packet. The PAD-I, it will send a offer packet to the client. The host may receive more than one PAD-O packet. Just like in DHCP, we could receive multiple offers. The host will look through the PAD-O packets and will select one of the packets, maybe based on the concentrator name, services offered, and it'll send a discovery, an active discovery request, a PAD-R on the selected access concentrator. And then the concentrator is going to send the active discovery session confirmation, the PAD-S. So the setup process, very similar, I think, to the DHCP process. May have issues that usually happen. The layer 3 features may not work if the layer 2 function has a problem. Layer 2 problem may result from a problem with layer 1. And this is where the OSI model comes in. Where is the problem? What's not happening? And that's what some of the troubleshooting commands are about, like show IP interface brief, the up, or up, down, whichever we have on those things. Debug, PPoE, different, the debug commands here, and you can use those when you work on the labs here. And then you're going to go in and create these things, and you see this is a real quick lab, 5 minutes here. GRE tunnel, this is a generic routing encapsulation. The advantage to it is that it uses can use multiple protocols. And again, do we need multiple protocols? There may be cases where we do. IPsec, the key on IPsec, the trick on IPsec here is that IP is the protocol that it uses. GRE, I think general is the term. So the different protocols that can be used here, session X.225. X.225 is an old protocol that is still around. I think it's used mostly in Europe. And then the transport UDP, network, GRE encapsulated IPv6, encapsulation GRE, IPv4, Ethernet, and then the physical layer when we have these things. So we want to encrypt these. This is obviously something that came from someplace else, but this is what IPsec. When we have IPsec, we add different elements to it. It's a structure that we use, and I talked about it a little earlier. Encryption. We pick our encryption protocol, 3DES, 3DES, AES, whatever is available, whatever is supported by the device itself. Authentication, the hash MD5 or SHA-1. Protection, the DHs over there are Diffie-Hellman. The negotiation protocol, authenticated headers, ESP, encapsulation security protocol. The AH is where we just check to be sure that we're talking to who we think we are, or we can encapsulate it and not do the authentication header, or we can do both. So the chunks that build an IPsec. Talk about here generic routing encapsulation protocol, GRE, unicast protocol, encapsulate broadcast and multicast traffic or other non-IP protocols. And this is something that's not going to happen in IPsec. Provides mobility service to mobile nodes, allow customers to leverage low-end residential gateways by aggregating the Wi-Fi traffic from hotspots. Use the customer premises equipment to bridge the Ethernet traffic coming from the hosts. When they're terminated on the service provider network, the host traffic will be terminated and the subscriber session initiated to the end host. High availability, SSO supported by IPv4 and IPv6 GRE tunnels. The functionality this one starts out, the existing low end, the same. Ethernet can be transported over IPv6 or IPv4. Tunnels can be configured as part of a single VLAN and support being provided only for a single VLAN tag. CPE, the customer premises equipment, has to insert the VLAN tag in these things. Can be configured with statically configured symmetric GRE key with a tunnel key in these things. So what we're talking about is, again, another structure that we can use to encapsulate, and in this case we have a little bit more capability. And this is why GRE, like IPsec, GRE tunnel is used to create point-to-point connections between two networks. Some of the benefits: data encapsulation, encapsulate packets that use protocols incompatible with intermediary networks, passenger protocols, so that we can maybe encapsulate, let's say we had IPX, encapsulate it and send it through an IP network, and when it got to the other end, we would use that within the protocols that are compatible transport protocols. Allows data to be sent across networks that otherwise could not be traversed, and here they talk about two AppleTalk networks through an IP network, IPv4 or IPv6. The simplicity lacks a mechanism related to flow control, and security by default can ease the configuration. GRE tunnels can be supplemented by IPsec suite protocols. We can add the IPsec protocols, the encapsulation and the hashing algorithms to it. It does multicast forwarding, which IPsec doesn't do. Can be used to forward multicast traffic, whereas a VPN can't do that. So a little bit of different things here. Virtual MAC addresses assigned to virtual devices. I think we've seen that when we used the HSRP and when we had the virtual IP and the virtual MAC address for these things. GRE tunnel will need to be configured with a virtual MAC address. Packet enters the tunnel, will accept the packet only if the destination MAC address of the packet matches the virtual MAC address of the tunnel or the broadcast MAC address of these things. So the MAC addresses have to match, and we use the virtual ones, and then you're going to have a little GRE configuration BGP, external BGP, Border Gateway Protocol, is the protocol that the internet runs on. And I think I actually do have one of these in Packet Tracer. It saves things for me, that you can see what it is. The single homed or dual homed, whichever we have used. Maybe I don't. BGP. This one is not one that I made up. It already had everything in it. You can see the configurations here. When we go into BGP, let's see if it's easier to see here. Show run. So we go router BGP 71, log, no synchronization, neighbor, and we give the neighbor IP address and their remote autonomous system number. So autonomous system 1, 172.16.0.1, this is 72.16.0.2. They're talking to each other. We have to manually specify the neighbors, unlike the others, the interior gateway routing protocols, that automatically found those. So we do the router BGP 71, log neighbor changes, no synchronization, 172.16, and you see how long it took to get the neighbor relationship. This is not a real fast converging protocol, which if you think about it, it runs the internet. You don't want it to be converging that fast, because how many routers go up and down at any instant on the internet? And if we try to do instantaneous convergence, we'd have a lot of flapping interfaces on these things. But we specify the IP address of the neighbors, and then the network that's on this device. We're advertising network 40 here is our network. So when we go over here and look at the routes, BGP is up, no IP route. We have a BGP route to 40, which was the other one here. And you notice that the administrative distance for this one is 20. And via how we're going to get to the 40 route, if I do a show run here, IP BGP, it's advertising network 10. Let's go over here and see if we're converged yet. We have them up. We have the neighbors. So IP route, and it's got routes to 10 and 40. 40, it says it's directly connected. 172 is directly connected. So we have those. It does have a little bit different configuration. It is the protocol that runs the internet. It's the only exterior gateway routing protocol that we use today. So it's an interdomain routing protocol. The ISPs, the providers of the internet, are assigned autonomous system numbers, and in our internal networks, EIGRP, we just pick our own autonomous system. Not going to be the case here. So it's an interdomain routing protocol, provide loop-free routing links between organizations. When there is a single linked home branch connectivity, this is obviously up here, is a dual linked. Is a term used to describe the enterprise branch in which only a single ISP provides the connectivity to the internet. Well, this is a dual link, not a dual homed. Single homed branch. BGP run over the Reliable Transport Protocol, TCP 179. So it BGP runs at the application layer, and it needs TCP and its ports 179 in order to do that, to make it work. Internally, we would use one of our internal gateway routing protocols, OSPF, EIGRP, RIP, if you really want, in order to do those. Path selection algorithm prefers the eBGP paths over internal BGP paths. Border Gateway Protocol can be both an external and an internal routing protocol. The internal routing protocol has an administrative distance of 170, I believe. With the multipath, non-virtual routing, and forwarding interfaces feature the algorithms modified to support multipath load sharing among native IPv4 and IPv6. If we had something like this, then we could do some load sharing with it. These are going to be very large routing tables. I want to turn it so we are connected to a router that is running BGP. If we do a show and we can't get into it, show I think it show IP BGP summary. Take a little bit because this is again a slow protocol with a lot of information on it. If we go over here, the table version, this is the number of routes that is in this router here, 4.69.184.193. So we have 23,213,134. When you say that they're big routing tables, they are big routing tables. And this one up here somewhere shows, I went too far, the BGP version, how many updates it's had. 23,213,419. And let's try that again. That's not what I really wanted to do with that. BGP sum. And maybe I'll have both of them and see how many changes it have in just a few seconds here. So now we have 230, that's going to change. So with 387 is the end number, and up here 149 was the end number. So you can get an idea of how many changes are happening constantly with these things. Get out of that. So BGP, internal, external, large, huge route tables go into these things, into the routing information base. Multipath we talked about. The different topologies that you might see with these things, autonomous system 1 and then the autonomous systems over here. External BGP, autonomous system 2, and it may be running internal BGP as the internal routing protocol if you really want to. It is kind of a pain to configure it, and I never figured out internally why you would want to run iBGP. It has a very high administrative distance, so anything else that's running is going to trump it anyway. EIGRP has an administrative distance of 90, iBGP has an administrative distance of 170. So it can be, and I guess that what we're showing here is it can be both an internal and an external. This here says autonomous system path of prefix A is 2.2.2.1. Therefore, prefix A is 4 autonomous system hops away. That's 2,2,2,1. BGP advertised routes in a similar way. It is kind of like the biggest RIP network in the world, because we have to manually configure the autonomous systems, but it talks to its autonomous systems. Is the only exterior gateway protocol. The interior gateway protocols preferred OSPF and EIGRP. It obviously is the thing that the internet's going to run on. This chart here shows the active BGP entries in the FIB, the number of routes starting back here in 1990, going up, and this goes through 2016. We're up to 600,000 entries in the forwarding information base. External peering, the sessions allow BGPs from different autonomous systems to exchange routing updates, and that's what that's all about. We saw the configuration on that. Expect the peers to be directly connected over the WAN. If they're not, you can have down here the configuration eBGP multi-hop to configure sessions from multi-hop routers that are farther down the line with these things. And loopback interfaces are generally preferred for establishing peer sessions. We want to add a loopback address and use that as the IP address for the sessions, because they don't go up and they don't go down, so you're not going to get flapping from the interfaces going up and down with them. The BGP attributes selects a single path as the best path to the destination host. That's what dynamic routing protocols do. Best path allows us to analyze the attributes, and the attributes you can configure are listed in the table, and I think that the table is the next. I stuck something in here. It's next here. This is just another image. External BGP. This one shows two different ways, two different links to get from the 100 to the 200. So we can configure these: router BGP 200, neighbor 13.13.13.1, remote autonomous system 100, and then neighbor 13 or 34.34.34.4, remote autonomous system 300. We have to specify the autonomous system number and the IP address to get to it. Not as not resilient, but not as automatic as you get in the others. This is the table that the other slide talked about for the BGP attributes. I probably should move that up, and then we'll go to the table again. Multi-homing here is the thing that I kind of have been talking about. That, yeah, I think that this is what you should do. We have our company here. We have an autonomous system, 65,002, and then the two different ISPs. If one of them goes down, then we have an alternate route to get to a second ISP. Connecting autonomous systems with more than one service provider, something that we might want to consider. And when we're talking about autonomous systems, we're not talking about a LeaderQuest or an eCPI. We're talking about a Spectrum. It's going to would have an autonomous system, and they would share their routes with the other autonomous systems. And then, you know, friend tells a friend tells a friend tells a friend, on down the line until finally we get into convergence. It's not a real fast convergence process. Avoid internet traffic. It says you must plan your routing configuration to avoid internet traffic traveling through your autonomous system, which might consume your bandwidth. Other internet traffic, not your own internet traffic, when we do that. When we do these. So suppress inactive route advertisement in BGP. If we have an inactive route, the BGP suppress inactive command allows us to configure that so that we suppress the inactive routes to any of our peers, which will then, going down the line, they're going to fall out eventually of the other route tables. An inactive routes that are not installed can be advertised by BGP in the rib to the peers. An inactive route is a route that's not installed into the rib. Routes are advertised through the common route aggregation. An inactive route advertisement can occur, and again, we can suppress those. The BGP states are idle, no connection between the neighbors. TCP connection has been attempted, but it hasn't been completed. Active, the TCP session's completed, no BGP messages sent. Open sent, the connection exists, and the router's trying to create a connection to a neighboring device. Open confirm, TCP connection exists, the local router had a message back from the neighbor router, and established is what we want to see. Both routers have agreed to form a relationship and can establish BGP messages with each other. So we finally do get to the endpoint here. Point-to-point WAN, simplest WAN topologies, hub and spoke, central site, single point of failure, mesh, the WAN topology, direct communication, everything's connected to everything else, and the number of connections that we need depending on the number of devices we're trying to connect to, the number of interfaces we're trying to connect to, or n, where n is the number of interfaces, n times n minus 1 over 2, to find out how many. 34, not so bad, but if you try, maybe you got 10 sites. What was that? That was 45. 10 times 9, 90 over 2, which is 45 connections to connect those 10 sites in a full mesh. MPLS, multi-protocol label system, was a way to speed things up. It allowed us to put a label shim into the packet before the IP address, so that the router, the device, didn't have to read deep into the packet and read the IP address. IPsec was a set of rules that we could define. We can pick what we're going to use. We had Diffie-Hellman there. We had whether we're going to use authenticating headers, ESP, or both, whether we're going to use DES, triple DES, or AES as our encryption protocol, and whether we're going to use SHA or MD5 for our hashing protocol. SSL, web browser used port 443, and we went through quickly how 443 and the HTTPS protocol ensures that we have a secure connection. PPP used LCP, link control protocol, to negotiate the priorities, and it monitors the availability of the link using requests and replies. Multi-link interleaving allowed multi-link encapsulation and fragmentation of large packets into smaller sizes, so that we can overcome the delay, any delay in the real traffic. So